Welcome to another episode of the Alpha Labs, and today we have a very special speaker cable from QSA Lanedri. Brand we didn't know, to be honest, but the producer reached out to us and said, we really want you to try this, it's something very special. And I said, yeah, but we also measure stuff, so are you sure? Yeah, I'm sure. This is very special, and I actually want you to measure it because I want to know what you find. Well, in this case, we make a video out of it. I'm not sure what I'm going to expect. We did a listening session, and it really sounds absolutely gorgeous. And I made some predictions. He filmed it. And I don't know if I'm right, so I'm really curious. I said it has low capacitance, it has pretty low inductance as well, but I asked about the geometry and he made a mistake. It has like 10,000 strands of copper, tint copper inside. It's also very heavy, as you can see, really heavy. And he thought it was isolated, but it's not isolated from each other. It's got to have some insulation, so I expect some capacitance. But I'm not sure whether I'm still correct because geometry is a little bit different than he told me. But anyways, I already measured the capacitance. It was like 200 picofarads, as you can see in the measurements, because I'm not going to do that again. But I had to recalibrate stuff, so I'm re-recording this, but as you can see, capacitance is around 195 picofarads, and that's extremely low. For a 3-meter cable, that's insane. But I had to recalibrate the connected part of these measurements, and I'm gonna connect it now. To measure the inductance and the impedance and the conductance. So let's see how that performs, because I think inductance will be, normally if you have very low capacitance, you have a high inductance. But I'm not sure, because it sounds very different, this cable. And in order to sound very different, there has to be something that we can see. So normally a speaker cable 3 meters is around 1.5 to 2 microhenries. Well, there you go. That's about average. We had some that had very low inductance, we had some that had higher inductance. Depends on the geometry, but this is actually pretty excellent. 1.8. It always fluctuates a little bit in the start, and then it will stabilize. And if it's around 1.5 to 2 microhenries, that's good. It's expected behavior. So blue is inductance. As you can see, most of them are around 2 to 2.5 even. Some are lower. The lowest is 1.2, 0.8. That's the install cable. Yeah, that's true. But it had higher capacitance, as you can see, because if the capacitance rises, normally the inductance drops. Yeah, 1.5 to 2.5, 3.5. Triada has very high inductance. 2.7. So this is really, really good. Yeah, 2 microhenries up to 175. So it's really good. It's I'm surprised. It's good. Now let's see what the impedance does. 0.0017. That's really low. Really, really low. Wow. Okay. I don't expect it to stay this low. We'll have to rise at some point. Yeah, it's already rising. This is tinned copper, so I'm curious what it will do, because you have some form of skin effect probably. Not at these low frequencies, but I'm not sure what the amount of tin is and what the amount of copper is and how thin these strands are. It will be very dependent on that in terms of impedance. But yeah, you can see it already. Then probably the conductance will drop also pretty fast if we measure it later. But in the base you have very low resistance, which is good. You want that. You want very low resistance in the base. And wow, that's sky high already. Yeah, it's really different how this measures. Really different. The phase shift is very quick. Curious how this will measure on a real speaker. Now you don't need that much energy in the treble, so that doesn't really matter, but you want very low resistance in the bass, and we have that, and that's what I expected as well, as you can see in his video if he ever publishes it. That's what I predicted. And it stops at 3 ohms. That's not bad. It's not exceptional, but it's definitely not bad, and the low resistance in the bass is as I predicted. Wow! What? 600? That's just nuts. It's crazy. $600 Siemens. Oh. Yeah, like I said, it drops off pretty quickly. You could see that in the impedance measurement. 300. God. Yeah, there's a load of copper in here. Loads and loads of copper. Yeah, this is impressive. Like 600 Siemens of conductance is crazy. This is a high power line. Yeah, the Nova does practically the same. It's really high. I think it's around 400. The Nova speaker. Conductance. Yeah, 400. This is 600. Honestly, you can hear that. The bass is just incredible. And I'm not sure if it's only the conductance and the impedance. I think it is. If you want good bass, you need low impedance. It's just what it is. And 600 Siemens will help with that. Yeah. Wow. Impressive. Well, now we got our LCR measurements. We got our impedance and phase. We got our capacitance, and we got our inductance, and we got our conductance, which is less important because this is literally another way of plotting the impedance. But I was just curious if I could predict what it is. Now we get to the interesting part. Now, if you have done this a lot of times, you can almost predict how it will plot if you know the LCR measurements. There is a direct relationship between the impedance and this plot on this loudspeaker. The lower the impedance, the flatter that line will be. Okay. Let's switch off this annoying beep. There we go. And go. Yeah, there we go. It is a little softer in the treble than I expected, but it does sound softer in the treble than Nova. That's funny. Let's see how it does around here. Okay. Zoom a little bit better. There we go. It is softer. Yeah. This is 20 kilohertz. So let's zoom in between 20 kilohertz. Yeah, there we go. I'll get this out of the way, then we can check it out and see if we can determine the character of this cable on this loudspeaker, that is. And the impedance curve of this loudspeaker is not the same as the TAD, so you have to keep that in mind. But as you can see, it's pretty much the same as the Nova up to 3 kilohertz. There it becomes softer, and I could actually hear that because it does sound a little bit more mild. It's very subtle because it's 0.05 dB. Now I want to try if I can actually make a measurement on this bad boy. This is the baseline. Now, one thing that's very, very important. Output is 0.4 ohms, input is 8 ohms. So I'm measuring now between an output like an amplifier and an input like a speaker. But the input impedance is just 8 ohms. It's not variable like a normal loudspeaker. So is it completely realistic? I don't think so, but this is how a lot of people measure. Yeah, I'll do it like this. This is okay. Wow. Very, very linear. Wow. Let me see, that's incredible. Freeze. Get it out of here very quickly because it's ridiculously heavy. Okay. Now that's one. Now I need to auto scale it. That's really, really good. This is 10 megahertz. This was the reference, so this is straight. It only dropped 3 dBm. It's incredible. This is very, very high bandwidth cable. Very high bandwidth. So let's see how I can make a boat plot, if that works. Reference. I think the reference was channel A. The normal output was channel B. And then we have the external, no, the generator on, of course, the input. I think it was this. Okay, let's go. Boat plots. It should drop around 4 dB, if I'm correct. So it should end minus 19, something like that. This is logarithmic scale, so keep that in mind, and that is linear scale, so it's different. But the whole idea should be the same. And we know from the impedance measurement that the phase shift is pretty intense, but that was without a impedance attached to the cable. There was no resistance at all. So the phase shift should be a bit different. Here we are at 10 kilohertz, 20 kilohertz, and still no phase shift, of course, then, because now we have the right impedances connected, and with the LCR we don't. Yeah, between 10 kilohertz and 100 kilohertz it drops a little bit, 1 dB. Minus 19, yeah, well, like I said, It's exactly the same, but this is logarithmic. So, good. Now, let's see. It didn't break. Thank you, Ruitenberg Consulting. It can handle more than I thought, but I'd rather not do this again with such a heavy cable. A little bit mild in the treble. Maybe that's because of the tinned copper. But it's very, very, very slight. So no shame there. Let's see, what can we do with... I want to see what the propagation speed is and what the propagation variance is. This is a hard one because now I need to connect it to the Tektronix scope. Yeah, I know this is a long video, but this is how we measure our cables that we get for review. At least when we have the time and support to do this. If we don't, then we don't, because you can see how much time it takes to do one cable. It's just a lot of work. It's swinging, I'm not sure why. Okay, the pulse is stable. Yeah, it's the connection, I'm afraid. Yay! We got it. Okay, don't pay attention to the waveforms because it's not that important. This is not a measurement for clean signals or anything like that. I hope I'm visible. I just want to know the delays. Wow, this is fast. I expected that. I think they're just straight wires. There's no twisting inside, I think. Not sure if it's the quickest cable I've ever tested, but it's very fast. That's for sure. Fluctuates a bit. I think if I tap the cable, yeah, see? And still people say that microphonics are not important. It's pretty well controlled, by the way. I've had way worse than that. Yeah, so 0.3 volts of loss is very, very decent. And we have a time that's 13.8 nanoseconds in 3 meters. Now this is a hard one because I've zoomed in twice. This is the normal screen. I've zoomed it in so you have a big one, and then I zoomed this part in to see if I'm on the right spot. Because I'm gonna check if there is a variance in delay. Now here you can see 13.88. It's quite about right. This is at 1 volt. Then I'm gonna go to 1/2 volt. And as you can see, it's still pretty much at the same spot. But I think this is actually the start of the rise around here. Now this is extremely hard to put it on the right spot. I think this is the right spot, 13.59. Now I'm gonna go to 1 volt and see if it changes. As you can see, it does change a little bit. I need to go to the right. Right about here. That's a different spot. Then I'm gonna go to 1.5. That's about the same. Then I'm gonna go to 2 volts. And you can see it is quite the same. We can go a little bit to the right. 13.82. Hey, that's the same as we had before. So it differs 0.5 nanoseconds. I've had 1 or 2 nanoseconds even in speaker cable. And most speaker cables change, to be honest. If we go back, you can see we have to go back here. No, it's not 0.5. It's 0.3. 0.3 nanoseconds of difference. And that's not bad. It's actually pretty good. So, these are the tests we do. I'm gonna try to do one more. I hope you found this interesting. I think it is. It is a very different cable, and it showed on the scope as well. The noise pattern is something I have to dive into, because it is very different from what I'm used to. All the response measurement says it's very high bandwidth cable, very low loss at higher frequencies. Maybe because of that it picks up broader noise. That could explain this, but all in all, conductivity extremely high, impedance very low, capacitance extremely low, inductance very well controlled. So yeah, it is a very nice product, and I really like its sound. Expect a review very soon. I hope you like these kinds of videos as well, in which we show you how we measure, what we measure, why we measure it. Hope to see you soon. Bye bye.